right, so we're gonna wrap up the topic today, I think. And we're going to kind of change gears just slightly. So we're going to talk about the ideal gas law today, which hopefully you've heard of before in chemistry or physics, potentially. So to start this off, engineering applications often involve substances in the vapor phase. So in the gas phase, most notable of these is of course air. It's all around us. So the evaluation of properties of gases is clearly important. And so that's what we're going to talk about now. So an equation of state is an equation that relates pressure, temperature, and specific volume of a pure substance in a given phase. And the ideal gas equation or gas law is an equation of state that relates properties of certain substances in the gas or vapor phase. All right. It's been experimentally shown that gases at low density closely follow the following relationship. So pressure times V bar is equal to RU times T. All right, where P is the absolute pressure. V bar is the molecular specific volume. That has units of meters cubed per kilogram mole, or units of cubic feet per pound of mass mole. T is temperature in absolute scale. So Kelvin or Rankine. And then RU is the universal gas constant. So this is equal to 8.314 kilojoules per kilogram times Kelvin, or in English units, 1.986 BTU per pound mole degree R, which is also equal to 1,545 feet times pounds of force over pound moles degrees R. A more convenient form of this equation is found by dividing it by the molecular weight or the molecular mass, which is capital M of the substance. So our molar mass has units of kilogram per kilomole or pound of mass over pound mole. All right, so we take our PV equals RUT and we divide both sides by the molar mass. All right, and it turns out that this term in particular is something useful or convenient for us. So V bar divided by M is the specific volume. All right, and so the reason for that is if we have V bar over M, we have meters cubed over kilogram mole. divided by kilogram per kilogram mole, which gives us meters cubed per kilogram. All right, so that is specific volume. Does this feel okay so far to everybody? All right. We also have an interesting note for this term. So, oops. So RU divided by M is often given the symbol R. So this is the ideal gas constant for the substance. So importantly, this is for the substance. So it's now not universal. It will change depending on the substance. All right. And this has units of kilojoules per kilogram Kelvin in SI. All right. So our final version of the ideal gas law that we will primarily use is PV is equal to RT. Okay. Okay. So we have another table for the things that are useful to us here. So we have our gas constants R. So just to remind you, R is equal to the universal gas constant divided by M. We also have the molecular mass. So if this is M, here's our column for M. You can find that on a periodic table as well. And then, of course, we have this for all kinds of substances that are gases. All right. So we will make use of this table. So for example, so the value of the ideal gas constant, so R, the ideal gas constant, depends on the substance. All right, so for example, so for air, we have that R is equal to RU over M. RU is 8.1 or 314. So this is always the same, kilojoules per kmol Kelvin. And then M, we can look up in this table. So we have 28.97. And the units are kilojoules per kmol. All right. So we get that R for air, and I'll put air down here, is equal to 0.287 kilojoules per kilogram. Okay. Yeah, sorry, I was just looking at that for this one, right? Sorry. Thanks. Yes, thanks. All right, and so this matches what is in this this part of the table. All right, so they do the division for you in the table, but this is where it comes from. Okay. Okay. Alternate forms of the ideal gas law can be obtained by multiplying with mass or the number of moles N. So we can make use of the following. So we can say that the volume is equal to mass times specific volume, which is also equal to the number of moles times V bar. All right, and here, N is the number of moles. Or pound moles. And then this is V bars, of course, the specific molar specific volume. All right, and then over here, we have obviously mass, and then this is specific volume. All right, so if we take our equation, oops, P V is equal to RT, and we multiply this whole thing times M, then I get that PV, well, let me do one more step. I have PMV is equal to MRT. And I know that M times specific volume is equal to the total volume. Equation is then just PV, where V is volume, is equal to MRT. All right, so that's one alternate form of the ideal gas law. And then if we do that same sort of process, but with the V bar version of this, so we have PV bar RU times T, and we're going to multiply this whole equation by the number of moles. Then we get the following. So we get P V bar times N is equal to N RUT. And we have that V bar times N is also equal to the total volume. So this version of the equation is PV is volume is equal to N R U T. All right, so one thing that I want to just highlight here is on the left-hand equation, the one in the yellow, when we have an M times RT, this is the gas constant that depends on the material you're using. And then in the orange, when we have N out front, that is the universal gas constant. Okay, so just be careful with that because that will change things quite a lot in your calculations if you're using the wrong version of R. Okay. Questions on this so far? Nope. Okay, good. Okay. Oh, sorry, before I go on. So a couple of other keynotes that I already mentioned, but I just want to draw your attention to it. Temperature must be absolute. So it needs to be Kelvin or degrees R. All right. Sometimes for certain problems, we can use either Celsius or Kelvin or Fahrenheit and Rankine, but that's only if we're doing delta T. So differences in those units are equivalent. But since we only have T in this equation and not a delta T, we need to make sure that we're using those units. And then also P is an absolute pressure, not gauge. So you want to make sure that you're including atmospheric pressure in there as well. Okay. All right. Okay. So now we're going to talk a little bit about compressibility. So our ideal gas law is called the ideal gas law because it's only applicable for ideal gases, as the name suggests, right? So we're basically going to discuss in this section, you know, what's the difference between an ideal gas and a real gas? And essentially the idea is that an ideal gas is a theoretical construct that doesn't actually exist in reality, but we have gases that get close enough that we can use this as a good model for what's happening in the gases that we actually have in physical space. So at very low density, which I mentioned earlier, gases are going to approach an ideal gas behavior, but that behavior departs significantly at higher densities. Okay, so if the ideal gas equation doesn't hold for a given gas, how much does it deviate? And that's something that we would like to know, right? So if we're using an ideal gas prediction, we'd like to know how wrong is our prediction, right? So in order to measure that, we're going to use a correction factor that we call the compressibility factor. And we give it the symbol Z. All right, the definition of Z is that it is the ratio of PV to RT, and it is unitless. All right, the reason for that is that our ideal gas equation is PV equals RT. We know that both sides of our equation have to have the same units. So if we divide the left-hand side by the right-hand side, the units go away. Okay? So for an ideal gas, what would Z be equal to? Any ideas? I heard 1. Yes, very good. So if PV equals RT, which it does for an ideal gas, then we would have a compressibility factor of 1. Okay? Okay. For real gases, the deviation from Z measures the deviation of the actual PVT relationship from the ideal gas equation of state. So for real gases, Z actually, let me back up. The deviation from Z equals 1 measures the actual PVT relationship. All right. So the figure that I have below here shows how Z changes with reduced pressure. So reduced pressure is given the symbol PR, and reduced temperature, which is TR, for 10 different gases. And this chart is known as the generalized compressibility chart. All right, and it looks like this. So we have our 10 different gases on here, given different symbols. This chart is actually a really nice case study and a well-made graph. All right, so we're using different symbols to show the different types of gases on here. It's all in the same color, so I could print this in grayscale and totally still read it. And then we have an average curve based on the data that is shown as a solid line. So our actual experimental points that we have are given as symbols. The kind of model or average behavior is shown as a line. And then a couple things to point out here. So we have our Z factor on the vertical axis here. We have reduced pressure. PR is on the horizontal axis. And then we have curves for the different reduced temperatures as these individual curves. So the behavior of each of the gases at a given temperature kind of collapse onto these lines, as you can see. So all of these symbols are represented in these groupings that we trace out the average behavior with the line. Does that make sense? Okay, cool. So let me just write down how do we figure out what reduced temperature and reduced pressure are. So PR is equal to the pressure divided by PCR. So this is a critical pressure. And same thing for temperature. So TR is equal to T divided by TCR. So this is a critical temperature. Okay, so you can see hopefully that as we get closer and closer to our critical temperature, so a critical temperature, a temperature equal to the critical temperature would be TR equals 1. That's when we have the worst deviations from the ideal gas law. Okay, so as T gets close to critical temperature, deviations are the most. Behavior. Okay. Okay. Now we're going to pivot and talk about internal energy, enthalpy, and specific heats of ideal gases. So an ideal gas is a substance whose pressure, temperature, and specific volume are related by the ideal gas law. That's what we've already discussed for this whole time. So we know that these three things are connected by PV equals RT. So that means that the specific volume we can rewrite as RT divided by P. All right. So because of this, we don't actually need a table to determine specific volume. And the ideal gas tables don't list pressure and specific volume values. Okay. So we don't need a table to find V for an ideal gas. And ideal gas tables don't list P and V values. Okay. So it can also be shown mathematically and experimentally that for an ideal gas, the specific internal energy depends on temperature only. And this was actually determined first experimentally by Joule. So that is the scientist whose name is what the energy unit is named after in 1843, which actually I find fascinating because 1843 doesn't feel like it was that long ago. But maybe I'm just old. So in this experiment that Joule did, what he did was he took 2 tanks and connected them with a pipe and a valve. So essentially he has a tank, another tank. They're connected with a pipe and a valve, like so. And he placed them both in water baths. So we have water baths. Okay. One of the tanks initially had air at a high pressure, and then the other tank was evacuated. So there was no air in there. He assumed it was a vacuum. And then when thermal equilibrium was reached, he opened the valve, which allowed air to pass from the pressurized tank to the one with the vacuum until the pressures equalized. During that whole process, he was measuring the temperature in the water bath. And because of that, he assumed that no heat had been transferred between the air and the water. So So since he also did no work on this system, he concluded that the internal energy had remained constant despite the change in volume and pressure. And so based on this information, he concluded that the internal energy of an ideal gas is dependent on temperature only. Okay, so this result has implications for enthalpy as well. So we have that enthalpy by definition is equal to internal energy plus PV. But if you remember from the ideal gas law, PV is equal to RT, right? So since our experiment showed that internal energy is a function of temperature, and since we can write PV as R times T, that means that enthalpy is also only a function of temperature for an ideal gas. So enthalpy is also only a function of temperature for an ideal gas. All right. What about the specific heats? So CV is equal to the change in internal energy with respect to temperature over a fixed volume. Since U is only a function of T, this becomes a total derivative. So we have du dt. And then Cp is equal to the change in enthalpy with respect to temperature for a fixed pressure. And since enthalpy is also only a function of temperature, this also becomes a total derivative. Okay. Tables A2 and A2E list values of CV and CP as functions of temperature for different ideal gases. Okay. All right. An important relationship between CP and CV for ideal gases may be obtained by differentiating the enthalpy equation. So if we have H is equal to U plus PV, or U plus RT. So this second part is only for an ideal gas, of course. Now we're going to take the derivative relative to temperature. This whole equation. So I'm going to put this whole equation into here. All right, so what I get is the following. So I have dH dt is equal to du dt plus ddt times RT. All right, can anybody tell me what this expression becomes? What about the left-hand side? What is dH dt? Yeah, it's just CP. So we have CP is equal to, what about du dt? That's CV. CV, and then what about the second term? R? Yeah, so this is just R. R is a constant, so it comes out of that derivative, and then dt dt is just 1, of course. Okay? So this result only holds for an ideal gas, all right? I'm going to write this probably a million times. So this is only for an ideal gas. All right. for any given ideal gas, we know that R is a constant, right? So R is equal to Cp minus Cv. And this must be a constant that is greater than 0. Okay, so that means that we know that R, Cp, and Cv are related in this way. Cp is always greater than Cv. Okay. We can also show that specific heats on a molar basis do the following thing. So we can also show that Cp minus Cv is equal to Ru. So these are specific heats on a molar basis. So they have units of kilojoules, kmol, okay. All right, so Cp is equal to Cp bar over m, and then Cv is equal to Cv bar over m. So m is the molar mass again. Okay. Okay. Changes in the specific internal energy and enthalpy of an ideal gas can be expressed as the following. So we have that du is equal to Cv dt. So I'm just taking that definition for Cv and splitting it up. And then similarly, dH is equal to Cp dt. So if we want to find the change in internal energy or the change in specific enthalpy, we would do an integral. So we'd integrate from state 1 to state 2 of du, which gives us u2 minus u1. And then the right-hand side of this equation is the integral from t1 to t2 Cv dt, noting that Cv is a function of temperature. All right, we can write the same sort of thing for enthalpy. So we integrate from state 1 to state 2. dH is equal to H2 minus H1, integral from T1 to T2 of Cp, which is also a function of temperature, dt. Okay. So if we wanted to do either of these right-hand side integrals, we would need to know how the specific heats vary with temperature. We would need to know what Cp and Cv as a function of T actually are. Table A2 lists the coefficient in a third order approximation of Cp, and it is of the form A plus B T plus C T squared plus D T cubed. All right, and we can use those functions to integrate internal energy and enthalpy equations that I've shown above. So essentially what we do is we would take this expression and plug it in to these integrals to carry those out, okay? Most of the time doing this integration is impractical, so we can use tables instead. Though it's notable that we only have tables for air, at least in the book, okay? All right, so those tables look like this. And it continues over here as well. So note that there are no P or V listings in this table, since internal energy is a function of only temperature and enthalpy is also only a function of temperature for an ideal gas. So what we do is we use the ideal gas law to obtain P and or V. And then just like how when we looked at other tables, if we are looking for something that's not a specific row, we're going to have to use interpolation with respect to temperature to find things that are in between lines, essentially, of the table. Okay. Okay. Constant specific heats. So this figure shows the variation of CP with respect to temperature for a number of gases. So if you remember, CP is equal to CP bar over M. And then also we have CP minus CV is equal to R. And I want to change this. This should be RU, not R bar. All right. We also have a table with this sort of information where we can see CP and CV with respect to temperature for a bunch of different gases. I've flipped off this table here, so it continues. So we have this for air, CO2, carbon monoxide, hydrogen, nitrogen, and oxygen. And so the simplest approach that we can do to integrating those equations for U and H would be to replace the specific heat functions by some constant average of the specific heat values. So essentially what we do is we write that U2 minus U1 is equal to the integral of T1 to T2 CV dt, which we will just call CV average times T2 minus T1. All right, and then similarly, we can do H2 minus H1 is equal to the integral from T1 to T2 of CP dt. And then this is CP average T2 minus T1. All right, so this is assuming that we have a constant specific heat. So ideal gas with constant specific heat. All right, where we take the average between the CP or CV at T2 and T1. Okay, so if we look at that plot up here, we can notice a few things about how CP changes with respect to temperature. So the variation of specific heat with respect to temperature is generally smooth, and we can approximate it as either a constant or linear over small temperature intervals. All right, so essentially if we go up to this plot, we could say, all right, at this location, it's fairly constant, obviously. Over here, it's pretty constant. Or we can say between some small interval, it's approximately linear, maybe here or here. Right, so that's a fairly reasonable approximation as long as we're looking at a fairly narrow temperature difference, okay? So using the average specific heat values can yield a reasonable accuracy over a small temperature range. Small is a very qualitative statement. Typically what we mean is a few hundred degrees or smaller, okay? So we can evaluate the averages in one of two ways. All right, so the first way is that we can evaluate CP or CV at the average temperature. So essentially we say, okay, let's identify the average temperature as T1 plus T2 divided by 2. And then we say that CV average is equal to CV at T average, or CP average is equal to CP at T average. All right. So that's one approach. The second approach is the following. So we can average the CP or C values at temperatures T1 and 2. So average the CP or CV values at T1 and T2. All right, so then we would say average is equal to CV at T1 plus CV at T2 divided by 2. And then the same thing for CP average. We have CP at T1 plus CP at T2 divided by 2. All right. Usually both of these approaches will give you reasonable results. So there's not one that's better than the other. You're free to use either one. So this is pretty simple and it's convenient when property tables aren't available. The results are reasonably accurate if the temperature range isn't big, and if the specific value of is properly selected. However, so this is reasonable. But if you have ideal gas tables, it is better to use the tables than to do this. And the reason for that is that it's more accurate. Okay. Okay, let's take a quick break and then we can do some examples and practice this. Okay. Okay, you guys ready to do some examples? No? Get ready. Prepare yourself. It's gonna be great. Okay. All right, so I have 2 examples for you. And I think we should be able to get through both of them. Okay, so the first one is we have air in a variable load piston cylinder device that's equipped with a paddle wheel. So I'm going to draw a picture of this first. So we have our piston cylinder device. And it's equipped with a paddle wheel, so I'm going to draw that this way. So this is our paddle wheel. And okay. And we have air in here. So this is our air. Inside of here. All right, and initially we're given that the air is at 500 kPa and 27 degrees Celsius. The paddle wheel is turned on by an external electric motor until 50 kilojoules per kilogram of work has been transferred from the wheel to the air. During this process, heat is transferred to maintain a constant air temperature while allowing the gas volume to triple. Calculate the amount of heat transfer required for this process. All right, so we have work, shaft work that goes in, So here's W. And then I'm going to just, we don't know what direction Q goes at the moment, so I am going to draw it this way for now. And then our system, I will draw as just the air inside of here. All right, so is this an open or a closed system? Closed. Excellent. Okay, let's write down what we're given. So we are given quite a bit of information. We're given that we have air. Which is important. We're given that it has a mass of 1 kilogram. Since it's a closed system, the amount of mass in our system is going to stay the same. We're given that P1 is equal to 500 kPa and T1 is 27 degrees C. We're also given that we have shaft work that's input and it's 50 kilojoules per kilogram. So that is specific shaft work, right? Because work should have units of kilojoules. So since we're given kilojoules per kilogram, that's specific. So we can get to just work by multiplying it by the mass. So we have 50 kilojoules per kilogram times our mass, which is 1 kilogram. So 50 kilojoules. Okay. We also are given that we are maintaining a constant air temperature. Which means this is isothermal. Which also means that T1 equals T2, which is 27 degrees C. That was already given to us. And we know that the volume is changing, right? So we have the volume 2 is equal to 3 times volume 1, right? That's this statement there. Okay, what we want to find is we want to find Q, right? So we want to calculate the required amount of heat transfer for this process. So that is find Q. Right? Okay, so we have our system here. It's just air and it's a closed system. So we have a fixed mass of air in our system. Since we are using air, we're going to assume it's an ideal gas. Okay. Okay, so we've got all of our assumptions, all of our knowns and unknowns listed here. We drew our system. Next thing we want to do is list out our governing equations. What are we going to use to guide this problem? And since we're trying to find Q, we're going to use conservation of energy. That's where Q shows up, right? So our governing equation is conservation of energy. Or that E2 minus E1 is equal to Q minus W. And remember that E is the total energy. So E is U plus KE plus PE. Can we neglect any of these terms, perhaps? Yeah, let's neglect kinetic and potential energy. Okay. Which means that this equation looks like the following. So we have that U2 minus U1 is equal to Q minus W. We want to find Q, right? So I'm going to solve this for Q. So I have Q is equal to mass times my specific internal energy at 2 minus my specific internal energy at 1 plus W. Now keep in mind, this is total work, right? Okay. We're given that we have shaft work input into the system, but we also have a volume that's expanding, so we have boundary work as well, right? So we want to recall that W is equal to work out minus work in. Our work out is going to be our boundary work. And then we're going to subtract off the shaft work input. Does everybody feel okay about that so far? Yeah. So it's expanding. Okay. All right, so our equation that we want to solve is that Q is equal to M times U2 minus U1 plus WB minus W shaft in. We're given the mass, so we know that, and we're given the shaft work in, so we know that as well. But we still need to hunt down U2 and U1 as well as the boundary work. Okay, so let's find U1 and U2 first. All right, so for U1, what we're going to do is we will go to table A21. We will look up internal energy for air at 27 degrees C, which is 300 Kelvin. Okay, so let's go there. Okay, so here is A21. We want to find 300 degrees Kelvin, which is right here. And I'm just going to take a clip of this to put it right by our work. All right, so from here we have that U1 is equal to 214.07 kilojoules per kilogram, right? So that's good. What about U2? And that orange. So at state 2, what is T2? It's the same, right? And we already talked about how U only depends on temperature, right? So what does this mean? It's U1, right? U2 equals U1. So because of that, that entire term just goes away. So we have Q is equal to M times U2 minus U1 minus W shaft in plus WB. So this term goes away since U2 equals U1. Does that feel okay for everybody? Okay. Another way that we could have come to this same conclusion is the following. So alternately, we could have said, well, U2 minus U1 is equal to CV times T2 minus T1. And T2 minus T1 is 0, right? Same idea. Okay. Okay, so now we just need to figure out the boundary work. Okay, so WB is by definition the integral from volume 1 to volume 2 of P dV. Pressure changes with volume though, right? So we need to know how pressure changes as a function of volume. So we need to know how P changes with V. But we have the ideal gas law, right? So we'll use the ideal gas law. So we have that PV is equal to mRT. And just solve this for P. So we have P is mRT divided by V, right? We know that temperature is a constant because T1 and T2 are the same. We know that R is a constant, and then we know that M is a constant because it's a closed system, right? So this is, oops, constant closed system, constant T1 equals T2 equals T, and then R is a constant by definition. Right? That's a material property. Okay, so we can substitute this into our integral then, and we have that the boundary work is the integral from volume 1 to volume 2 of mRT divided by V dV. All right, so this whole thing is a constant, so it can come out of the integral. All right. And so we have mRT integral of dV over V from V1 to V2. So what do we have for this integral? Yeah, natural log of volume. Evaluated from V1 to V2. So I'm gonna write this over here. So we have mRT natural log of V2 minus natural log of V1, which is mRT times natural log of V2 divided by V1. Right? Okay. So I have everything. I have mass, I have R, I have T, I have V2, and I have V1. Right? So when I plug in all of these things, I get that WB is equal to 1 kilogram times 0.287 kilojoules per kilogram K times 300 K times the natural log of 3. because V2 is equal 3 times V1. And then Q is equal to minus 50 kilojoules plus WB, which is 44.6 kilojoules, which is greater than 0. So what does this mean? So this means that heat was input into our system. Any questions on the process for that problem? Yeah. So that was a convenient choice. So for posterity, for the recording, how did we know to use PV equals MRT instead of NRT? The reason for that is because we were given mass in the problem. If we were given number of moles, then you'd use NRT. So I just chose that one out of pure convenience. Yep. And technically you could use PV equals NRT if you really wanted to convert the mass that we're given into the number of moles that works out to be using the molecular mass. Yep. Yep, because molar mass will give you the number of the kilograms per mole, and we have the number of kilograms, so then we can just use that to figure out how many moles that works out to be. I chose the path of less suffering. You'd get the same answer though. Okay, other questions on this problem? Okay, let's do one more. Okay, so we have two tanks connected by a valve. One tank initially contains 2 kilograms of carbon monoxide gas, at 77 degrees C and 70 kPa. The other one holds 8 kilograms of the same gas at 27 degrees C and 120 kPa. The valve is opened and the gases are allowed to mix while receiving energy by heat transfer from the surroundings. The final equilibrium temperature is 42 degrees C. We want to use the ideal gas model with a constant CV and determine the final equilibrium pressure and the heat transfer for the process in kilojoules. Okay. Okay, so our system is going to also include this valve and piping system. So let me just correct that slightly. So this is our system. All right, so this is a closed system again. All right, and I'm going to call this tank A and tank B because tank 1 and 2 gets a little confusing because we want to talk about states 1 and 2. So I'm going to switch it to A and B. Okay, so let's write down what we know. So we know that mass A at state 1 is 2 kilograms. We have temperature of our gas in tank A at state 1 is 77 degrees C. And then we have our pressure in tank A at state 1 is 70 kPa. And then for tank B, our mass at state 1 is 8 kilograms. And our temperature of tank B at state 1 is 27 degrees C. And then our pressure of tank B at state 1 is 120 kPa. Then we have at equilibrium, which I'm going to call state 2. We have that T2 is equal to 42 degrees C. And we want to find P2 and Q. Okay. We're going to make a couple of assumptions here. So we're going to assume the following. We're going to assume carbon monoxide is an ideal gas. We're going to assume constant specific heat. And we're going to assume a closed system, so no leaks. And last but not least, we're also going to assume that these are rigid tanks, which means that our volume's not changing, so we don't have any boundary work, right? Okay. Okay. So we want to find P and we also want to find Q. We're going to kind of use two different governing equations to sort those things out. So to find P, what do you think we should use? What governing equation should we use? We talked about it a lot today. So we're going to use the ideal gas law. All right, so we know that P2 V2 is equal to M R T2, right? We would like to find P2, right? And we are given actually, let me call this M2. Okay, we are given T2, that's our equilibrium temperature. R is a constant that we can look up for carbon monoxide, so that's easily attainable. What about M2? What should we use for M2? Any ideas? So I think you guys both said the same thing at the same time, but we're just going to add up the masses from the two tanks. Is that what you both said? Okay, cool. So we're going to use the mass of tank A at state 1 plus the mass of tank B at state 1. All right, so we've got 2 kilograms plus 8 kilograms is a total of 10 kilograms. All right, the reason for that is because all of our mass is at the same state in the end, so we can just lump it all together as the same mass. Okay. What about V2? We don't necessarily have anything about the volume, right? So V2, we know that the tank is rigid, right? So we know that V1 is equal to V2 because the tank is rigid. Any ideas on how we could find V1? So we're going to just apply the ideal gas law again, but for state 1 and solve for V1. So we can use the ideal gas law at state 1 to find V1. Okay, so what we're going to do is the following. So we are going to say, okay, we know that PA at 1 plus VA is equal to MA at state 1 R times TA1. And we can write a similar thing for PB at state 1 is equal to M times B1 R TB1. All right, so we have two masses of carbon monoxide and they're both at different temperatures and pressures. So essentially what we need to do is we need to find the volume occupied for tank A and the volume occupied for tank B, and then the total volume for state 1 is the sum of those things. Okay? So V1 is equal to VA plus VB. And we're going to use this expression to solve for VA, and we'll use this expression to solve for VB. Okay? Okay, so let's do that. Okay, so for VA, we have that MA1 RTA1 divided by PA1 is our VA. We have all of these things. So we have 2 kilograms of mass times R is 0.2968. So this was from the table A1. Kilojoule per kilogram K. So this is from table A1 for carbon monoxide times 77 degrees C plus 273. So this gives us our temperature in Kelvin, divided by 70 kPa. And I'm going to convert this. So 1 kilopascal is 1 kilonewton per meter squared, and 1 kilonewton per meter square per meter is 1 kilojoule. So let's cancel some things out. So kilograms cancel, Kelvin cancel, and then kPa cancel. We have, I need another color. We have kilonewtons cancel, and then one of the meters cancels. Oh, I'm sorry. No, they don't. They multiply. And then kilojoules cancel. So we end up with cubic meters at the end of this. All right, so when we carry out all that multiplication, what we get is 2.97 cubic meters. All right, and then we can do that exact same thing for VB. So VB is MB1 RTB1 over PB1. All right, so we have 8 kilograms times 0.2968 kilojoules per kilogram K times TB1 is 27 plus 273 Kelvin divided by 120 kPa, and we get 8.91 cubic meters. So this means that V1 is equal to VA plus VB, which is, sorry, 8.91 is the total. I wrote this one down wrong. So this one for VB is actually 5.94. Sorry. Okay, so going back to this equation here, so we have P2 V2 is equal to M R T2. So I can solve this for P2 now. I have M R T2 divided by V2. And now I have all of the parts of this that I need. So I can fill that in. So I have 10 kilograms is our total mass times R, which is still that 0.2968 kilojoules per kilogram Kelvin, times T2 is 42 degrees C plus 273 converts that to Kelvin. And then we're dividing by our V2, which is 8.91 meters cubed, which gives us 105 kPa. All right, so we have solved one of these. So this is P2. So we've solved that part. Now we want to find Q. So now find Q. All right, to find Q, we're going to use our conservation of energy because that's where Q shows up. So we have conservation of energy is that E2 minus E1 is equal to Q minus W, right? Our total energy is internal energy plus kinetic energy plus potential energy. Can we all agree to neglect kinetic and potential energy again? Yes. Okay, so we're going to neglect these, which means that our equation is U2 minus U1 is equal to Q minus W. Do we have any work in this system? No. So we have no boundary work since they're rigid tanks. And then we also have no applied work. Okay. And we, of course, want to find Q, right? So we want to find this. All right. So I am going to write my left-hand side broken out. So I have mass times my specific internal energy at 2 minus my specific internal energy at 1 is equal to Q. All right. And I'm going to also rewrite this as my mass A at 2 times U at A2 plus MB2 UB2 minus mass of the tank A at state 1 times the internal energy at state 1 tank A plus mass of tank B at state 1 U B at state 1 is equal to Q. Right? We know that for state 2, our internal energy is the same everywhere, right? So it's at equilibrium. So since 2 is at equilibrium, we can write this as M2 times U2 minus, and then I'm going to keep all this the same. So I have MA1 UA1 plus MB1 UB1 is equal to Q. Okay, we already know from the last part, we know what M2 is, we know what MA is, and what MB is for state 1. For UA1 and UB1, we know the following. So for an ideal gas, we know that U2 minus U1 is equal to the integral from T1 to T2 of CV dt. All right, so I am going to kind of algebraically massage this a little bit. So I'm going to say M2 is equal to MA1 plus MB1, right? So our final mass is just the sum of the masses in tank 1 and tank 2 at the start. And I'm going to factor this by MA1 and by MB1. So I have U2 minus UA1, and then U2 minus UB1 is equal to Q. Is that okay for everybody? Okay, good. So now I can use this equation in the orange, the integral from T1 to T2 of CV dt, for each of these. All right, so if we assume constant specific heat, then this integral goes away and we get CV times T2 minus T1, right? So I am going to just apply that in here. So I have mass A1, and then I have CV times the quantity T2 minus TA1 plus MB1 times CV T2 minus TB1 is equal to Q. Is everybody with me so far? Okay, so we have all of these things, except for we need to pick CV. So we need to use the average CV for both of these. We'll have to use different CVs since the average will be different, since TA1 and TB1 are different temperatures, right? So we know MA1, we know T2, we know TA1, we know MB1, T2, and TB1, but we need to find these CVs to use. Okay? So these are averages. So this first CV average is going to be approximately equal to CV at 300 K plus CV at 350 K divided by 2. This one is 0.744 kilojoules per kilogram K. That's from the table. And then this one is 0.746 kilojoules per kilogram K. And we get 0.745 kilojoules per kilogram K. And actually, so you could do this two ways. You could calculate two different CV averages depending on the difference between T2 and the temperature in tank A, and then T2 and the difference between temperature at tank B. Or you can say, I will take the average between the extreme temperatures in the system. So our maximum temperature that we see is 77 degrees, and then the minimum one is 27 degrees. So we're going to just use the same CV average for both of them. Okay. And you can see that the difference in CV between those two temperature extremes doesn't really change very much, right? We're looking at 0.744 versus 0.746. So that's pretty reasonable to do. Okay, so plugging that back in, we get that Q is equal to 2 kilograms. So this is MA1 times 0.745 kilojoules per kilogram K. times T2, which is 42 minus 77 Kelvin, plus 8 kilograms times 0.745 kilojoules per kilogram K, times T2, which is 42 minus 27 K. And we get 37.25 kilojoules, which is greater than 0, which means heat is input into the system. Okay. Any questions on that one? No? All right. Well, that is the end of this unit.